Hello, my name is John Krochmalny, and I've developed these visual tutorials to accompany any technical training format that might be delivered. In this presentation, we cover the basics involving alternating electric current, how it's generated and used. Also, in this presentation, certain properties involving alternating current electricity are introduced. There are three learning outcomes associated with this presentation. Number 1, describe voltage induction. Number 2, describe alternating current and voltage. And number 3, describe single-phase and three-phase voltage induction. Our understanding about voltage induction starts with the magnet. Perhaps we all know of the magnet's force of attraction. In this graphic, we have opposite poles of two magnets facing each other. Having these opposite poles of magnets facing each other, we see that there is an attraction force operating toward each other. This attraction results in the movement of magnets toward each other. We may also understand that when two identical poles of magnets face each other, there is a repelling force. The repelling force results in the movement of the magnets away from each other. This invisible force of attraction and repulsion is attributed to the lines of flux existing within the magnet. Since it is the lines of flux that gives the power of magnetic force, we can understand that the greater amount of flux lines a magnet has, the greater the force of attraction or repulsion. Also, by looking at the graphic, we can see that these lines of flux come out of the North Pole and enter the South. Since there is a force of the magnet resulting in a movement, we can logically determine that the magnets have energy. Since energy can be converted from one form to another, we can convert this magnetic energy into other forms of energy. It was Michael Faraday, a British scientist, that experimented with this energy conversion back in the early 1800s. He took a voltage meter and started to measure the voltage induced into the meter leads as the leads were passed through the magnetic lines of flux. Faraday discovered that voltage was induced into the meter leads and read by the meter whenever the leads were passing through the flux lines. The greater amount of flux lines being passed through the leads, the greater the amounts of voltage pressure were measured. This phenomenon is called voltage induction, the conversion of magnetic energy into electrical energy. Faraday's original experiment may have included passing conductors through flux lines. Realize that the same voltage induction can happen by passing magnetic lines of flux across conductors. In this graphic, we see a bar magnet placed on a pivot and is able to rotate 360 degrees. Notice that the lines of flux are coming out of the magnet's north pole and enters the south. Here we see the voltage meter being applied with its conductors placed to the north pole section of the magnet. Notice that in this position, the flux lines are not affecting the voltage meter leads. By spinning the magnet counterclockwise, notice how the lines of flux build across and then disappear from the voltage meter leads. Notice again how the lines of flux build across the voltmeter leads in a clockwise rotation between 0 and 180 degrees rotation, and counterclockwise between 180 degrees and 360 degrees rotation. It is important to understand that there is voltage pressure building in the conductor due to the flux lines. Regardless of the direction that the flux lines are passing through the conductors, either clockwise or counterclockwise, the effect is the same. Voltage is induced in the conductor. As we could suspect, using this system of electric voltage induction, we could conclude that there is times when voltage is present and times when it's absent. It is this type of electricity that is used most in power systems. Let's compare the rotation of the magnet's flux lines into a capturing conductor per degree of rotation. In this graphic, we see a magnet that can rotate 360 degrees. The graph on the right can record the voltages induced into the circuit. Rotating the magnet 90 degrees counterclockwise, we see the voltage rise from 0 to a maximum value. Now notice that in this graphic, the magnet has rotated from 90 degrees to 180. We can also see that as it does so, the flux lines start to disappear across the capture conductor. The measured voltage goes from a maximum value down to 0. Rotating the magnets from 180 degrees to 270 degrees, we can see the flux lines enveloping across the capture conductor and inducing a maximum voltage. Notice that the voltage appears and disappears when the magnet is rotated. It is important to understand that there's a maximum voltage appearing in these types of systems and is seen on the right side of the graphic. Voltages either above or below the value of 0 represents voltage pressure and is necessary for current to flow. The complete rotation of the magnet returns back to its original position, in this case 0 degrees, and the voltage induction process starts anew. The voltage in this type of generating system is known as alternating current, AC voltage. Sometimes you have it, sometimes you don't, depending upon where the magnet's flux lines are appearing across the capturing conductor. Applying what we've learned about voltage induction and alternating current, AC, we see that in this latter diagram, 120 volts AC is powered to the R1 load. Let's consider what happens to amperage when voltage is induced into a circuit. As we already know, there needs to be a pressure difference to initiate flow of any matter. We can then predict the relationship existing between voltage pressure differentials and its flow rate. Starting at 0 degrees, we see the lines of flux away from the capturing conductor. In this position, there is 0 voltage and 0 amperage. Here, we see the magnet rotated counterclockwise 90 degrees. As it does so, voltage is induced in the capturing conductor. The greater the lines of flux results in the greater voltage pressure. Notice that with increasing voltages, there's also an increase in amperage flow. Rotations from 90 to 180 degrees results in falling to 0 voltages and corresponding amperages. Rotating from 180 to 270 degrees results in a building of voltages and amperage values. Whether this voltage or amperage is located either above or below the 0 line on the measuring graph, it still represents power to the circuit using it. After 360 degrees of rotation, the process begins anew. This is perhaps the best example of what alternating current and voltage is and how it's generated. Referring back to our ladder diagram, we can see 120 volts AC or alternating current as our power source to the circuit. We can now imagine that the voltage and current appearing in this circuit is pulsing according to the frequency due to the spinning of the magnet and its flux lines inducing voltage pressure into the conductors. In this ladder diagram, we can understand that all of the circuit's pressure is coming from the L1 terminal of the power supplied. The N is the neutral. Neutrals do not have voltage, but they serve as pathways that amperages take when voltage pressure is applied. This example is referred to as a single-phase power source circuit. The current resulting from the voltage difference comes from one point in the circuit at one particular time of measure. This is referred to as a three-phase power generating system. We have the same bar magnet that can rotate 360 degrees, but notice that there are a total of 3 capturing conductors capable of voltage induction and current initiation. To make it easier to understand, we can assign colors to each capturing conductor. L1 is brown, L2 is orange, and L3 is yellow. Starting at the 0-degree mark, notice the position of the flux lines in the L1, L2, and L3 capture conductors. Relate these flux line positions to the measuring graph located to the right. L1 has 0 volts, L2 has close to maximum volts, and L3 has little volts. Beginning our counterclockwise rotation, we see the flux lines building across and disappearing from each capturing conductor, and it does so in sequential order. This induces voltage pressure in L1, followed by L2, followed by L3. After a complete rotation, the voltage induction process begins anew. This is an example of a three-phase voltage generation system. 3 separate circuits, each with its own voltage available to power circuits. As mentioned before, a single-phase circuit has its voltages passing through the circuit on one direction at one time. In the ladder diagram on the left, we see L1 providing the voltage and the current at any time. Notice that the middle diagram has 2 voltages, one appearing on L1 and the other appearing on L2. When L1's voltages are higher than L2, the current travels from left to right. When L2's voltages are higher than L1, the current travels from right to left. This is also a single-phase circuit since current only travels in one direction per unit of time. The right ladder diagram involves a 3-phase motor. Notice comparing this diagram to what we know about 3-phase systems. Current is passing among L1, L2, and L3 during the same units of time. Alternating current and voltages are used primarily for powering most of the world's electrical needs. The countries of the world may have different voltage standards and frequencies, but the generating concepts will be the same: the use of magnetic lines of flux to induce voltage pressure into conductors, which in turn induces an amperage flow.